So this video, we're going to talk about some examples of an optimization of how things are done. Yes, you can use low-Q traditional approach. You're going to have a lot of ports and therefore transistors, and it's expensive. And if you're trying to do more relaxed consistency model, the LQ-based design, if you are really trying to be more relaxed, is in fact more difficult to implement. Again, because you're trying to catch a more complicated case. It has to satisfy multiple conditions, and therefore catching that condition takes more circuit monitoring. So what can you do? The key thing, the example that we're showing really is demonstrating a key principle, which is how you use better negative tests. So what does all this mean, right? We're monitoring some situation. And when some conditions are met, you run the risk of violating correctness concern, of violating a correctness constraint, and you need to redo squash instructions and re-execute. But very often you have cases where you can easily detect that this is not going to be a problem. Okay? So you want to control false positives. Okay? And what's a false positive? That you detect that this is a situation that you need to squash, but it really isn't. Okay, so if we look at alpha 21 364, right, for instance, they prevent cases where 1 and 3 are happening, and some of them will be false positive. You squash them, but this is easy. Detecting just 1 and 3 is easier than detecting 1, 2, and 3 simultaneously. So you're allowed some false positive. That's fine, so long as you don't allow too many. You're not going to slow down the system too much. And you want the test case to be cheaper. And the problem with conventional approach is these CAM unit. They're too expensive. And why do we have these units? Because we're doing address match. Okay. Really what we're saying is search throughout all the queues, see if you match any address. And when you don't match any address, you can say, fine, nothing is happening. They're not to the same address, I don't have to worry about them. But testing for the address match is actually very expensive. Every address is 64-bit or something like that, a lot of bits, and matching them is expensive. So what we tried out, and this is a paper that we wrote many years ago, it's a completely different approach. We call this timing-centric. So we're more worried about testing the timing condition than worried about address. The observation is this: yes, we have an out-of-order processor, but that doesn't mean they're wildly out of order. In fact, even with an out-of-order processor, you can run a program and see that the actual execution order is very close to program order, to in-order execution, with some occasional out-of-order execution. Suppose, what if you run the program and the execution sequence happens to be program order? Okay, think about that extreme case. In that extreme case, you can say, I don't need to test anything. There is not going to be any order violation. Okay. It's impossible to violate write serialization if I executed all my memory instructions in program order. So what we do is we actually track the age of the youngest issued load. So when we issue an old load, we compare that with the youngest issued load so far, and if we don't detect any out-of-order loads, then we can say everything is fine so far. Okay? And if there is, and to make sure that this is the case more often, you make the address go to different banks by some bits, by looking up at some bits of the address. So even though globally the load and stores are not necessarily in order, but if you take the address, you split them into a couple of banks, within each bank, the memory accesses may follow program order with higher probability. So that's what we're trying to do. We divide the address into a couple of banks. The degenerate case is globally just one bank, but if you have a couple of banks, and then you monitor the memory accesses within those banks, and all you're trying to do is to compare age. And why is that good? Age is a small number, okay? It's a narrow number. How many instructions can you have in flight? How many memory instructions can you have in flight at any moment? Hundreds, you know. So to differentiate them, you have a couple of bits rather than address, which is much more, much wider. So we compare narrow number for the most part, okay? And as a result, as a side benefit, we don't have a size limit on load queue. We're not keep tracking of everything in a big queue. We're simply recording the youngest load, and therefore we don't have to limit on the size. So this is how things work. Let's take an example. So again, in single thread application, we want to make sure load and store are executed in correct order. But in multiprocessor case, we need to guarantee write serialization, which is to prevent this case that we're showing here. Two stores, two loads happen out of program order. In between, there's an invalidation to the processor issuing those two loads. Okay, and this would violate write serialization, and sequential consistency would be something else. So all of implementation are somewhat conservative. They over squash a little bit to make sure you're never wrong. You may lose performance a little bit. It's just the way you're being conservative is different. Okay, the way you're over squashing is different. So let's think about this. So in a regular system, whenever you have a load, you compare to earlier loads. Okay, to all of them. Compare address to see if there's a match. If there's a match, you do something. If there's no match, everything is fine. In our system, we rely on the table. And this is the main thing. And there's a little bit of optimization over here that you can ignore for now. And this table is separated into different entries. It's a hash table. You take an address, you hash the address, and you go to a certain entry. Another way of thinking about it is I'm banking all the addresses. I go to the bank, and I put my age there. But before I put my age there, I compare my age with what is already in there, which is the youngest load that happened to that hash entry. Okay? So if the table's entry is younger, then I have a problem. Because two memory access, the younger one, possibly to the same location, not necessarily because it's a hash table, and there is a younger one already happening, okay, I may have violation. Let's say I just replay. If I do that, I can guarantee that I will have no order violation, because it's always a younger one in program order happens later. If that's not the case, I am squashing some load to restore the reordering. Okay. But if I go to the entry, that one is older than me, fine. Nothing needs to be done. I put my address, I put my age in there, and things keep on going. So what happens in this case is if I really don't have a wildly out of order execution, then every time I issue a memory transaction, I go to the table, I heard back the answer that, okay, no violation happens. It will work pretty well. Okay, so the detail it is, so whether this works very well depends on the detail. We can simulate it and see, and this is what we find out. So here is a very interesting comparison. We're comparing this with another often used technique that's called a Bloom filter. So some of you may not know what a Bloom filter is, and this is very simple. Let's explain this. Bloom filter is a membership test, and it does this following thing, which is it will never give you a false negative. The memberships can have false positives. What does that mean? Suppose I have a collection of data, and a membership test is I have a new number, X. I want to know if it's already in my set. Okay, how do I do this? To have an exact membership test, I have to compare to this number, to that number, and so on and so forth, right? And that's expensive. This set may be very large. A Bloom filter is, you can think about it, the typical implementation is just a hash table. Suppose I have this set, and I represent it by a hash table. I take the first element over here. Let's call that A, let's call that B, and this is a bit vector. Okay, so I take A, I operate on it with my hash function. That will give me an entry, and I will set the bit to 1. And you have B, I will get another entry, and I will set that entry to 1, and so on and so forth. So if I have a test that I want to conduct, and it's about value X, I go through the same hashing function, and I look into the entry. If the entry is 0, that means none of these elements over here can be X. Otherwise, it would have been set to 1. Okay, so if the result turns negative, I know it's correct. But what if the hashing gives me, let's say, to this entry? It's not here, maps to an entry that's 1. Too bad. I don't know for certain. But the test is potentially positive. But the positive can be false positive. And that's Bloom filter. And the idea is these tests are cheaper. Rather than go through all the elements doing comparison, I can simply do a hash and get an approximate answer. And oftentimes this is very good. So why is this useful, right? Well, imagine what we're doing with a store queue, load queue checking. Again, we have lots of entries. This may be your load queue. What do you have? Addresses, and plus other information, but I'm just showing address. Now I have a new, so A, B, C, a lot of addresses. And now I have a new address, X. I need to search certain in load queue, right? Certain direction. Only those addresses that are younger than me, for instance. Is there a match? What I want is to compare. Is X equal A? Is X equal B? And so on, right? This is the same problem that Bloom filter is trying to solve. So instead of that, we can have a hash table, have all the memory elements set their bits, corresponding bits, and when I have an X, I go through the Bloom filter test first. Okay? That's the general idea. It's more complicated than that in real life because in load queue, for instance, I keep on adding more entries, and if I keep on adding more entries to my Bloom filter, eventually it will be all filled with 1, and it will never work anymore. It will always tell me it's potentially in there, right? So there are all kinds of problems. counting bloom filter. Instead of 0 and 1, I set a value to it. If one entry is put into the queue, I increment the counter. When an entry is removed from the queue, I decrement the counter, and so on and so forth. So that's the detail. But what we can compare that is what we just did, which is put the address into a hash table. Not put the address, put the age into a hash table. And if the age is in order, meaning the new age that I'm putting in is always younger than the age that is already there, then we don't have to do any checking. Okay, everything is in program order. So how does that help? Well, if that test already says we're fine, not going to have any out of order, not going to have any violation, then we don't have to do anything. If that says we have violation, then we can either conservatively squash or go through a more detailed test to see what we can do. See, we can use bloom filter to do the same thing with traditional store queue, load queue. And this is the amount of filtering you can achieve by increasing the bloom filter size. And it kind of saturates very quickly. Okay, we see about, 70% or so, or not even 70%. Doesn't really matter. As you increase the size, it doesn't reduce that much more. But with what we call the youngest load age register, if I have one youngest load register, that means this table has only one entry, one global entry, then I'm already filtering better. That's integer application, floating point application. I'm already filtering better than a kilobit of bloom filter. If I further have 8 such youngest load age, I can filter out almost 95% or close to 100%. So most of the time, the situation is, if you separate the address into a couple of banks, most of the time you would see that there is no order violation at all. You don't even need to worry about, are they to the same location? Okay, so this filtering is very, very effective. And that is what you can do to ensure no order violation. Okay, all of these cases, there's no order violation. And for the few cases where it's less, the 2% that you fail this test, you can do a couple of things. Of course, you can squash and replay. That will perhaps impact your performance, but you can also do some more testing. And in our paper, we did discuss this in detail, which I'm not going to cover in this video. So that's really some sort of digression into how this is all done. Conventionally, we're using load queue, address comparison, expensive, but that's not really what you need to do. You can do some neat tricks to make this thing cheaper than it might have been.